Hi everyone. Good morning. Welcome back to another CMB Bharat Cosmology seminar. My name is Fazlur Rahman and I'm a postdoctoral researcher at Texas A&M University. Today our speaker is Dr. Srinivasan Raghunathan from the University of Illinois, who is going to talk about cosmic microwave background science from South Pole Telescope and beyond. So it's my pleasure to introduce Srini here. So Dr. Srini earned his PhD from University of Chile, and later he worked as a postdoctoral fellow at the University of Melbourne and then at the University of California. So he joined University of Illinois in 2021 as a survey science fellow at the Center for Astrophysical Surveys. Srini has been actively involved in the South Pole Telescope (SPT) and the CMB-S4 collaboration. He currently serves as the co-chair of the CMB secondaries and cross correlation analysis working group for the SPT collaboration and the co-chair of the cluster analysis working group at CMB-S4. So it's my pleasure again to welcome Srini to our seminar today. Over to you, Srini.
Great. Thank you. Thank you, Faslu. Hope let me make sure everything is clear here. Can you see this probably?
Yeah, we can see that.
Okay, great. Okay, awesome. All right. Yeah, thanks so much, Faslu, and everyone for the opportunity to talk about CMB with SPD and beyond. And thank you so much for the really nice introduction as well. Okay, all right, I'll get into this. So I'm going to mainly say about how we can constrain cosmology and astrophysics using cosmic microwave background as the observable from South Pole Telescope, which like Fazlul mentioned, is the main instrument that I work on. And also, I will mention some of the future surveys, which I hope will be really useful for CMB Bharat. So here I have some snapshots from my talk. So these are some of the results that I will focus. And as you can see here on the left, so these are recent constraints on the epoch of reionization using the kinematic Sunyaev-Zeldovich effect. And then on the right, I'm showing a work in progress where we are trying to constrain both cosmology and astrophysics, which in this case is baryonic feedback, using the thermal Sunyaev-Zeldovich effect. And I will discuss these things later. Okay, so I'll get into the talk directly. So I have some introductory slides for CMB. I don't think I have to motivate this particular team in terms of CMB, but I just want to give my point of view, and I also thought that there might be grad students, so it will be useful. So once I introduce CMB, I'll get into SPT, and then I'll get into KSZ and TSZ results. Okay, so what you're seeing here is the timeline of our universe. You might have seen different versions of this particular picture. I like this version because this kind of emphasizes many of the science cases that I'm going to talk about. So on this figure on the left side, we see inflation. So inflation is basically, we think it's the beginning of everything. So inflation is followed by a period of hot Big Bang. So inflation predicts a lot of things. In fact, my thesis was on detecting gravitational waves from inflation. So inflation predicts a lot of things, and most of those things have been observed. Unfortunately, many other theories also predict these observables. So detecting this inflationary gravitational waves is regarded as a smoking gun of cosmic inflation. And we have been working towards detecting this, including this is one of the main science drivers for CMB Bharat as well. So you all know about this. Okay, so there was inflation, and then for the first 400,000 years, universe was extremely hot, and as a result, it was ionized. So photons cannot free stream easily, meaning the mean free path for a photon is extremely small. And as a result, when a photon tries to travel, it interacts with a free electron, and it changes its direction. So this keeps on happening for the first 400,000 years. And after 400,000 years is approximately the time when the universe was cool enough, because during this time, the universe was expanding, and as a result, it was cooling down. So around this time, universe was cool enough, so neutral atoms can form, and by neutral atoms is mostly just hydrogen. So we don't have any more free electrons, and as a result, photons can free stream towards us from this particular time, and this time is called the epoch of recombination or the surface of large scattering. So this is really the time when CMB is free streaming towards us. And after that, not much happened. The universe was just filled with neutral hydrogen. So this is the period of dark ages. Not a lot of interesting things happened during the time, but at some point, things started to collapse under their own gravity. And as a result, it started, the universe started forming first stars and galaxies. So this period is around redshift 10 or slightly higher than that. So this is a time when first stars and galaxies are forming. And the light from these first stars and galaxies, so these are UV photons, and these UV photons are energetic enough that they can actually kick an electron from this neutral hydrogen that's filling the universe. So this period is called the epoch of reionization, because the universe was ionized before, it was neutral, and then it's now reionizing. And after this, bigger and bigger structures started to form. So this is via hierarchical growth of structures, where we have galaxies, galaxy clusters, and all the cosmic web that we observe with different telescopes. So I want to highlight this particular period because this is really the observable that I'm going to talk about. So like I said, so this is 400,000 years after the Big Bang. Cosmic microwave background is free streaming towards us from this particular epoch. So this is redshift around 1100. So CMB, as a result, is basically the remnant radiation from the Big Bang. It was predicted by George Gamow in 1940s and accidentally discovered 20 years later by Penzias and Wilson. So having CMB is really one of the most compelling proofs that the Big Bang model of the universe works. So this CMB is an extremely homogeneous and isotropic radiation, roughly a backbody spectrum peaking at 2.7 Kelvin. And at the time of recombination, so recombination was not instantaneous, so there was a window to that. And during that window, there were still free electrons. And then these free electrons now, when they interact with CMB photons, they induce polarization into CMB photons. So this is polarization due to Thomson scattering. So it's only linear polarization. So CMB does not have any circular polarization, any primordial circular polarization to it. Okay. So the other important aspect of CMB is that the CMB is really like the most distant light that we can ever observe. So in any direction, it is the most distant light. And as a result, CMB basically forms a backlight for everything that we know in the universe. So besides learning about the origin, okay, yeah, there you go. So besides learning about the origin of the universe, CMB actually serves as a backlight to study about the contents and the evolution of the universe. So basically, CMB photons are interacting with everything that we know in the universe. These interactions lead to these the secondary anisotropies in the CMB, which I will talk about more later. So only a very small fraction of the CMB photons are affected by these interactions. And so these secondary anisotropies are not as bright as the primary anisotropies. Okay, so here is a beautiful compiled picture of the cosmic microwave background observed by 3 different satellites. So on the left, we see an image from COBE. So this is a satellite that was launched in 1990s. This is a satellite that first observed the anisotropies of the CMB. And as you can see, the resolution is actually pretty coarse. I think it's roughly around 7 degrees. And then 10 years later, WMAP was launched. You can see the improvement in resolution. And after that, Planck was launched, and you can see the resolution has improved significantly from going from left to right. So Planck had roughly 5 arc-minute resolution. So that's roughly the angular resolution of these maps. Okay. So as cosmologists, what we normally do, and this is also what we do within SPD, is that we observe the millimeter wave sky. So we basically map the temperature anisotropies in a given region of the sky. And then all we do is just take so on the left, you're seeing that image. So then what we do is we just take the power spectrum of it. So, and what I mean by power spectrum is just take the Fourier transform, for example, in Python. Take the absolute value of that Fourier transform, square it. So that is basically the power spectrum. So it's normally a two-dimensional power spectrum, but then we can bin it in azimuth, and then we get this plot that I'm showing here on the right. So that's the temperature power spectrum of the CMB observed by Planck. Okay. So the data points here are Planck observations, and the curves are the model that was fit to these observations. So basically, as cosmologists, what we do is we take image of the sky in millimeter wave band, take the power spectrum of it, and then compare our observations with theory using different Boltzmann codes. And then we come up with the model for the universe, which is basically the Lambda Cold Dark Matter model. Okay, so that's pretty much what we do, particularly for students. Okay, so why is this really powerful? And I want to emphasize why these things are great using some of these plots. Okay, so I'm going to show a lot of these kinds of plots. So I'm pretty sure you might have seen this, but I'll quickly say what this plot is. So the horizontal axis in this plot is a multipole, which is the inverse of angular scale. So when we're looking at the left side of this plot, we are looking at extremely large angular scales in the sky. And then on the right side, we're looking at small angular scales. So the vertical axis is the power, which is nothing but just the variance in the image that I was showing before. Okay. So what we do is, so this is a 2-point correlation function, but in Fourier space. So what we do is we pick 2 points in the sky. So there is an angle to this. We measure their correlation, and then we take 2 other points, 2 other points, 2 other points, and then we take the mean of all of those things. So then we just take a different set of two points. So we just shrink this angle, and then we make several measurements, and then we take the mean, and then we make plots like this. Okay. So when we're looking at this plot, so what you're seeing here particularly is the temperature power spectrum of the CMB. And when we're looking at this, we can infer a lot about the universe. So for example, when we're looking at the first few peaks, we can learn about the curvature in the universe, the spatial curvature, or we can learn about matter in the universe. For example, if matter is mainly baryons or it's dark matter. And I just want to show an example here. So this is exactly the same plot, but what I'm doing here is I'm fixing lambda CDM. I'm fixing all the other parameters except the baryon fraction in the universe. Okay. So the matter density is fixed, but I'm just modifying if the matter is dominated by baryons or by dark matter. Okay. So if baryon density changes, it actually, in the early universe, it slows down the pressure waves. So basically what's happening in the early universe is that matter is trying to collapse under gravity, whereas the radiation pressure is pushing things out. So it's basically like a harmonic oscillator. So that's all our universe is. It's a damped harmonic oscillator. So when we are changing the baryon density, we are basically slowing down the pressure waves. And as a result, on these plots, so the oscillation actually, the amplitude of the oscillation actually increases when we increase the baryon density. So it's basically like an harmonic oscillator. So the universe now stretches more, and since it's stretching more, it takes more time for it to relax. So as a result, the phase also changes when we modify the baryon density. So this is one of the parameters that we can really measure very well with CMB observations. And here is an example showing how the power spectrum changes when we change the baryon density. But I also want to give you an intuition of how this actually happens when we look at the maps. Okay, so what you're seeing here is now a simulation where lambda CDM is assumed. All the other parameters are fixed except the baryon density. So you see some hot blobs and cold blobs. So these are anisotropies in the CMB. And as you can see, the size of these blobs roughly correspond to 1 degree on the sky. So that's roughly the size of the universe at the time of recombination. So now you can see on the title, so that's the baryon density that I've assumed. So now I'm going to change the baryon density. As I increase the baryon density, you can see that the shape of these blobs are now either increasing or decreasing depending on if the baryon density is either higher or lower compared to the fiducial value. Okay. So like I said, like you're seeing on the left side, when we increase the baryon density, so these blobs become, the amplitude becomes higher, so the blobs become bigger and bigger. Okay. So this is just an example showing how these how the power spectrum is sensitive to this particular parameter. So similarly, we can also look at the polarization power spectrum of the CMB. So like I said before, CMB is polarized, but it's only partially polarized. So the amplitude or the power in the CMB, in the polarized CMB maps will be much lower than the temperature maps. And as a result, this blue curve is much smaller, much lower than the red curve. But the red curve, similar to the red curve, the blue curve also gives us a lot of information about the universe. So, for example, when you're looking at the small scales, we learn about, for example, light relics in the universe. And then when we're looking at the larger scale information in polarization, we actually learn about epoch of reionization, as I will show, as I'll discuss more later. And of course, finally, we also have the B mode polarization because it looks like the magnetic fields. And B mode polarization has two sources. One is due to gravitational lensing coming from low redshift, and the larger scales comes from inflation. Of course, we don't know the scale of inflation. That's why we have three different curves here. Okay, so those are all mostly just theory curves, assuming lambda CDM, and here are observations. Okay, so these are compiled observations from different experiments. So you can see data points from Planck, ACT, Atacama Cosmology Telescope. We have measurement from BICEP, measurement from Polar Bear, and also SPD, South Pole Telescope. And there is a curve here, and the curve is actually the Planck lambda CDM model. It's not a best fit to all of these different experimental data points. But what you're seeing here is this curve, the lambda CDM curve predicted by Planck observations is a really, really good fit to all these other experiments. Okay, so again, you can see all of these data points lie extremely nicely on this theory curve. So, which is great, which is amazing. So now we can ask a question like, why do we have to keep doing this particular science if everything is just so well determined? So, of course, it's not all that's clear here. So, for example, there is a deviation there on small scales in the temperature power spectrum, and I will discuss why that is. But the real key thing here is this. So this is why I think we should be doing new surveys. So even though these data points are all lining up with Planck lambda CDM curve, which is great, there are so many mysteries that remain. So for example, some of the constituents of lambda CDM, dark matter, dark energy, we actually have not a good knowledge about those constituents. We don't know about inflation. We're still trying to figure out neutrinos and so many other things. Okay, so even though lambda CDM works, we actually have no idea about lambda CDM. We don't know much about the constituents of the lambda CDM. So it's basically just a mystery that this model works for the universe. And the other important point that I think why we should be doing these new surveys is because there are so many tensions. So these are cosmological tensions. And a couple of famous ones are the Hubble tension, which is the Hubble constant determined by supernovae, the low redshift supernovae measurements, and the ones from high redshift CMB observations don't actually match. So similarly, there is also a structure growth tension, which is basically called the SI tension, and I'll touch on that a little bit later. So these tensions could be a probe of new physics, or this could be just systematics in these different cosmological observations, that we are considering. So these are all the reasons why I think we should be doing these new surveys. And here I just wanted to show the timeline of the ground-based CMB experiments in particular. I want to emphasize that these are just ground-based experiments. Of course, if it's space-based, CMB Bharat will also be here. So the green ones are the ones that are being that are based in Chile, in the northern Chile, and the yellow color ones are the ones from South Pole. Okay, so from Chile you can see Atacama Cosmology Telescope, which actually finished observations, and the analysis is going on right now. And we have CLASS from Chile, which is another CMB polarization instrument. And then Simons Observatory is just starting. Then we'll have SIGAT Prime. Then we'll have the advanced SO. And then at the South Pole, we currently have BICEP and South Pole telescopes that are operating. So South Pole telescope is expected to operate until 2029, but we might have an upgrade to our camera around 2026. So yeah, so these are basically the landscape of CMB experiments that are current, and that'll be in the future. And of course, you also have CMB-S4, which is really like the next generation CMB instrument, which is supposed to be both in Chile and in South Pole. But the South Pole component of CMB-S4 is currently in flux, so we don't know what's going to happen. And here is just nice images of these instruments. So on the left, you see South Pole telescope. So this is really at the geographic South Pole. And then you see on the right, you see ACT, SO. These are all in northern Chile. And then in the bottom, you see CMB-S4, which is both in South Pole and in Chile. Okay, so now let me get into South Pole telescope. So here is a really amazing image of South Pole telescope taken by one of our winter rovers last year. So what you're seeing here, okay, yeah. So on the bottom right, you see the South Pole telescope. So it's a 10-meter diameter dish located at the geographic South Pole, observing the sky in millimeter wave bands. But then you also see this amazing southern lights, which is the Aurora Australis. And then this image is actually like a time lapse. So what you're seeing here is basically an eclipse. That's in the middle. I think my cursor is not visible, but I hope you can see the eclipse here. So this is also one of the astronomy pictures of the day last year. So besides doing CMB science, you can also collect a lot of amazing pictures of the southern sky from here. Okay, so like I said, it's a 10-meter diameter telescope. It operates in 3 different bands, 90 gigahertz, 150, and 220 gigahertz, with roughly an arc-minute resolution. And currently, we are in our 3rd generation, which is called the SPD-3G survey. So 2007, we started SPD-SZ. It went on for 5 years, and then we installed polarization sensitive detectors. So it's called the SPD-Pole survey. And currently, we are in the SPD-3G phase. So it's really a 3rd generation camera. And as you can see here, the number of detectors basically went up by an order of magnitude compared to SPD-SZ. So we have extremely deep observations of the millimeter wave sky. Okay, so here is the South Pole Telescope collaboration. So this is a photo that was taken earlier this year. We are roughly 100 scientists, equally divided between senior, postdoc, and students, and roughly span 20 institutions across the globe. And I want to show these images to convince you all that SPD is really amazing. So what you're seeing here is a real image of the sky taken by WMAP. So this is roughly 30 square degrees from WMAP. So you see some dark spots and cold spots. So these are all primary CMB. Okay. So if you look at the same region with Planck, you can see that's how things change. So you can see the improvement in resolution and also the improvement in noise levels. Okay. So this is WMAP to Planck. So you see these blobs become slightly sharper because of the improvement in angular resolution. But when you look at the same region with SPD, this is how things look. Okay. So again, we see those large-scale blobs, the dark spots and the hot spots and the cold spots. But we also see some really small hot spots and cold spots. Okay. So the majority of the large-scale features that you're seeing here they're all just cosmic microwave background, the primary anisotropy of the CMB. But these small white spots, so these are all actually galaxies. So these are all mostly quasars and dusty star-forming galaxies emitting also in the millimeter wave band. So for astronomers, so these are real signals. For example, many people have taken these galaxies and made follow-up observations with ALMA and JWST to find extremely high redshift lensed galaxy systems. But for us, these are mostly contaminations. So we have to do a lot to get rid of these things to do cosmology. So those are the dark spots. Sorry, those are the bright spots. But now we're looking at these dark spots. So these are all clusters of galaxies. Okay, so they appear dark because of this effect called thermal Sunyaev-Zeldovich effect, which I'll discuss later. So currently, SPD-3G is so sensitive that we don't just see quasars and galaxy clusters, but we also actually see asteroids. We see Starlink satellites, and we see so many other millimeter wave transients. Okay, so Lots of other kinds of science also can be done with SPD. Okay, so what exactly are these?
I had one
secondary-
question.
Yeah.
Yeah, which region of the sky is this?
I'll show you which region in a little bit. I have a plot there.
Okay, and what is the resolution for SPD?
So it's 1 arc minute.
Okay, okay, thank you. Okay.
Yeah, so it's 1 arc minute. So for example, all of these clusters and these galaxies, they actually appear as point sources for us. So we don't have the power to actually resolve these sources. So what has to be done will be to collect these candidates and then make high resolution follow-up observations of these with, for example, ALMA or other bigger telescopes. Yeah, thank you for the question.
Okay, thank you.
Okay, so now let me briefly introduce the secondary anisotropes of the CMB, and I'm going to mainly just talk about three things, because those are the dominant effects. So the first one is gravitational lensing, so which is basically just the bending of light because of matter that we have in the universe. So we have galaxies and structures in the universe. So we have the cosmic web, which has dark matter, and these dark matter, basically it's just bending the path of the CMB photon. Okay. So this has been observed. So this has been detected with very, very high significance. And we have cosmological constraints from these things from all the major CMB surveys right now. So the next effect is a thermal SE signal. So this is the reason why galaxy clusters appear as dark spots in our maps. And the reason they appear as dark spots is because of this. So imagine looking at a region of the sky. Okay. So you have CMB photons traveling towards us from the surface of large scattering. But when there is a galaxy cluster in the middle, so galaxy clusters are normally hotter than average. So they have ionized, these are ionized regions, and they have free electrons. So when the CMB photons interact with free electrons, they actually get an upscatter. So they get an energy boost. And as a result, these CMB photons basically move to a different frequency band. So if you're looking at a region of sky with just 150 gigahertz telescope, the CMB photons there will appear as missing because they just gained energy and moved to a different band. So as a result, at the location of galaxy clusters, we will have a decrement in our CMB maps, and this decrement is a function of frequency. So this is actually how we detect galaxy clusters in CMB surveys, and this is the thermal Sunyaev-Zeldovich effect, which is just the inverse Compton scattering of CMB photons of free electrons. So we have galaxy clusters and halos that have free electrons. But these halos are not static. Everything in the universe is always moving. And that gives rise to this second effect called the kinematic Sunyaev-Zeldovich effect. And as the name sounds, it's kinematic because it is proportional to velocity. Okay. So if the halos are moving towards us, so in the radial direction or in the line of sight direction, if they're moving towards us, CMB photons get a Doppler blue shift. And if they're moving away from us, CMB photons get a Doppler red shift. Okay. So this is a second effect besides the thermal Sunyaev-Zeldovich effect, and it's slightly fainter than the thermal SZ. But we can use these signals to learn a lot about so since these signals come due to structures in the universe, when we detect these signals, we can actually learn about structure formation. So for example, we can learn about structure formation using gravitational lensing. We can learn about galaxy clusters using thermal SZ. We can learn about velocities using kinematic SZ. Okay, and we can do a lot with all of these signals. In fact, these are the reasons why there is a deviation in the temperature power spectrum when we are looking at small scales. Okay, so the lambda CDM curve does not take into account these secondary anisotropies, and that's the reason the theory curve is lower compared to the data points here. Okay, so more about SPD. So to answer your question, so this is the region that I showed before.
Okay.
Okay, so SPD has three different surveys or three different footprints. So the green region is our main footprint. So we call this the main 1500D. So it's 1500 square degrees. And then we have the yellow color region, which is basically roughly 2600 square degrees. So we call these the summer fields because this is the region that we observed during austral summer. And then this year, we went wide. We actually observed this red color region, which is roughly 6000 square degrees. So you can see the noise levels that are quoted in the table on the right. So in total, we have extremely deep observations over roughly 10,000 square degrees of the southern sky. And we have really good overlap with galaxy surveys. We have really good overlap with upcoming CMB surveys. And we also made targeted observations of some of the deep fields, like the Euclid deep field and Sphere-X deep field. So these are some of the properties of the SPD survey. And this map that you're seeing here, so that's again the map from our main 1500D field. And SPD is so sensitive that SPD can achieve the same depth as Planck in just 1 week. So Planck has observed for several years, but SPD can achieve the same depth in just 1 week. And we already have more than 5 years of data that we are analyzing right now. So you can now imagine the improvement in noise levels. But of course, Planck has observed the full sky, but SPD is focusing on a smaller patch. So that's something that we need to take into account. But the bottom line here is that we have extremely deep observations of the millimeter wave sky. So as a result, we can make extremely good cosmological measurements. So what you're seeing here on this plot here, so this is basically the ratio of, sorry, not the ratio. This is actually just a signal to noise of every mode that we can measure in temperature and E-mode cross correlation, E-mode polarization, and then lensing. Black here is a comparison for Planck. So you can see on large scales, left side of the plot, Planck always wins because of the sky fraction, particularly in temperature. But you can see when we go to small scales, SPD is way better than Planck, okay, in temperature, polarization, and lensing. And as a result, we will have significant improvement in cosmological parameters that are sensitive to small scale information. Okay, so significant improvement compared to Planck on small scales. And then on the plot on the right, I'm showing the lensing power spectrum. So this is basically the noise in the lensing power spectrum. So the gray curve is a signal, and the different curves correspond to noise from different experiments. So you can see Planck is there. So Planck is the black curve. So Planck is way noisier compared to all these other surveys. But you can see SPD, which is shown in green, is just way more sensitive than any other experiments that are plotted here. So if you look at our lensing map is basically has a signal to noise greater than 1, up to something like L of 800 or so. Okay, so SPD lensing maps are extremely deep. The other key point about SPD lensing maps is that our polarization noise level is so low that we can construct lensing map just with polarization. Okay, and we are at a regime where the quadratic estimator, which is the standard CMB lensing estimator that the community uses, is no more optimal for us. So we have to do better. So we have to introduce some optimal estimators to improve the signal to noise. And this is extremely crucial for doing B-mode science, which I'm showing here. So this is basically what we can get as a constraints on the primordial B modes. So this is basically the tensor to scalar ratio. So here, showing here in the bottom, as a function of here. So this is primarily for BISUP. Okay, so this is the constraints that we can get with BISUP and Keck as a function of here. But you can see when we are at this regime, BISUP is now basically just limited by lensing. Okay, so BISUP cannot do better without getting rid of lensing induced B modes. Okay, so you can see here with SPD, we can improve the constraints on sigma of R by roughly a factor of 3 compared to what BISUP can achieve by itself. Okay, so this is really key. So if we don't have SPD, BISUP really cannot improve much. So that's why we have this new collaboration called the South Pole Observatory, where we use SPD's lensing measurement to de-lens the BISUP B modes. Okay, so this is a new collaboration that we formed in the last few years. Okay, so basically just based on all of these things that I've showed, so SPD does not have a single science driver. We have so many science drivers. Like for example, we can do inflation science, we can do cosmology, we can learn about reionisation using kinematic SZ. We can do cross correlation with galaxy surveys and with upcoming intensity mapping surveys. We have detections of high redshift clusters in galaxies. We have now sensitive to millimeter wave transients, and we can actually do AGN monitoring and detect asteroids and so many other things. So this is basically the cosmological constraints that are expected from SPT. So this plot here, the plot on the top. So this is actually showing the 6-parameter lambda CDM volume. Okay, so you don't have to think too much about this plot, but you can take that as a figure of merit for constraining all the 6 parameters jointly. Okay, so what I'm plotting here is the number that we get for SPD compared to SPD and other experiments compared to Planck. So anything above 1 is better. And what you're seeing here, these red points, so this is basically the constraints that we expect from the full SPD 10,000 square degree survey. And you can see it's roughly a factor of 100 better than Planck. And the other nice thing is that SPD is roughly the same as first 2 years of SO, which is going to be really, really crucial for map level comparisons. And then, of course, we have CMB-S4, which is like roughly a factor of 1,000 better than Planck. But then there is a window between SPD and CMB-S4, which is nicely being filled with SPD 3G plus or advanced SOs. So these are all the next planned CMB experiments from ground. Then at the bottom, I'm showing the expected constraints on lambda CDM and extensions from SPD compared to Planck. And the takeaway message here is that most of these parameters improve by roughly a factor of 1.5 to or more compared to Planck. So these are expectations. And we recently released our measurements from the first 2 years of data. So what you're seeing here is the measurement of CMB lensing and CMB E-mode power spectrum from the first 2 years of SPD data. So you can compare the SPD results, which are shown in black, with all the other experiments. So most of them are just consistent with each other, but SPD is really sensitive on small scales. So this is really the best measurement of E-mode power spectrum and lensing power spectrum at small L greater than 2000 or big L greater than 200 so far. So then we can use this to derive cosmological constraints. So one crucial point about this particular release is that this is a polarization only release. So we didn't even include temperature here. So obviously adding temperature improves all of these things way more, but this is a polarization only result. And you can see SPD is just way better than all the other things here, like Planck or ACT as shown here. Okay. So this is the first time that we actually see the Hubble constant tension just with polarization measurements. So you can see, for example, Hubble constant here is plotted in the bottom left. So what we get from SPD is shown in blue, and then we have the shoes measurement shown as the dotted lines. So you can already see that the 3 to greater than 3 sigma tension in Hubble constant there. And then on the right, it's basically just emphasizing the Hubble concentration and the SI tension. Okay, so this is one of the recent SPD results. So now let me go a little bit into doing reionization science with KZ, and then I'll talk to, I think I'll probably spend 10 minutes on this and then 10 more minutes on thermal SZ. Are there any questions so far? Okay, I'll continue, and I guess we can discuss later.
Sorry, can I ask a question?
Sure, yeah, go ahead.
Yeah, how does the lensing signal to noise compare between SPT and ACT?
Yeah, so you can even see that here.
Yeah.
Okay, so I don't have a plot here, but if you look into this reference that is given here, okay, so let me just say this first before that. So here on this plot, you see the ACT lensing noise. Okay, so that's shown here in the purple color, and SPD is green. So you can see the noise level is just way better than ACT. But of course, ACT has way bigger sky coverage. So when we translate this into band powers, the F sky matters. So ACT will have really good error bars. But if you look into this paper that's referenced here, so there is a plot that shows how we compare to ACT. So basically on small scales we beat ACT, but on the larger scales ACT is better than us because of the sample variance.
Okay, yeah, thank you.
Yeah, but thanks for the question. Okay, so let me continue now with KZ. Okay, so like I said before, so KZ is one of the secondary anisotropies of the CMB, and it's a Doppler boosting of CMB photons due to free electrons, but these free electrons are in motion. Okay, so this effect has two sources. So one is a low redshift source, and the other one is a high redshift source. So the low redshift source, by low redshift, I really mean redshift 0 to redshift 3 or even 4. So these are halos in the local universe moving mostly towards each other due to gravity. Then in the high redshift, so these are the patchy reionization bubbles that are just caught up in the bulk velocity flow in the universe. Okay, so both of these signals, so both of these regions have free electrons, and these free electrons are moving, and they give rise to the KSZ signal. Okay, so I'm more interested in the reionization part, but there has been so many recent papers also on the low redshift part, which mostly can be detected by cross correlation with galaxy surveys, because these are mostly halos in the local universe that are moving. Okay, so let me focus on this. So what is this? So reionization is the period when light from the first stars and galaxies reionize the universe. And when I talk about reionization, I'm mostly just talking about the hydrogen reionization. Later in the universe, there was also a helium reionization, which I will not touch here. Okay, so when first stars and galaxies are forming, like I mentioned earlier, so these are energetic UV photons. So these UV photons basically kick an electron from the neutral hydrogen that was filling the universe. So this is the epoch of reionization. And here is a simulation showing how this process might have happened. So what you're seeing here in this image, mostly it's just black. So these are all just neutral hydrogen locations. But you also see some bubbles. So these are the locations where we have ionized electrons. Ionized medium, so we have free electrons. So now we can see, as I roll the movie, these bubbles are growing over time, meaning reionization is happening. So most of the universe is now becoming reionized. So these bubbles are becoming bigger and bigger, and they are coalescing. And at some point, they will stop when the universe is almost fully reionized. Okay. So this is how reionization should have happened, or this is how we think it should have happened. And what you see here is that this reionization is a very, very patchy process. Okay, so it's an extremely non-Gaussian process. And that patchy, non-Gaussian, so those two words are a key for some of the next slides that I'm going to show. Okay, so how we can probe reionization using CMB. So there are different ways to probe reionization. So one is this very simple thing that we can picture. So what's happening here is that, so we have some intensity. So the CMB photons, let's say they have some intensity, and they're traveling towards us, but now there is a cloud containing free electrons. So this cloud has an optical depth. And as a result, the intensity is now going to be attenuated when you have a cloud. And it's going to be e to the minus tau. So in power spectrum, it's going to be e to the minus 2 tau. Unfortunately, what happens here is that you can either suppress this amplitude by having a very, very high tau, or you can suppress this amplitude by having a very low normalization. So it's extremely just degenerate with the amplitude of the power spectrum. So this is almost impossible to do anything in terms of reionization. So the next signal is the large-scale E-mode polarization bump, which is due to additional polarization that was generated at the time of reionization. So this is extremely large scale. So this is roughly multipole less than 10, because that's the size of the universe at the time of reionization. Okay, so you can see now tau is basically proportional to the amplitude of this E-mode bump. So if we observe this E-mode bump, we can learn a lot about tau. It is extremely hard measurement to do from ground, because we don't have this full sky coverage to measure these large scales. So this can only be done from space. For example, this is one of the targets for CMB Bharat. Okay, so it's great, right? So Planck has measured this. So this is good. However, that's not the full picture. The reason is because this particular bump has no information about the process of reionization. And here is a nice plot emphasizing that particular point from Planck. So what you're seeing on the left is the ionization history of the universe. So the horizontal axis is the redshift, vertical axis is the ionization fraction of the universe. So 0 meaning universe is fully neutral, 1 is when universe is fully ionized. Okay, so you can see at very high redshifts, universe is neutral, and at very low redshift, universe is fully ionized. But then in the middle, something happens. Okay, so that's the process of reionization. But you have so many different curves. So there is a curve even which says universe reionized, went back to neutral, and then came back again. Okay, so you have all of these signals, but when you take all of these signals and translate into an E-mode bump, they all just sit on top of each other, which basically says that what we're measuring with this E-mode bump is the integrated optical depth, which is not sensitive to the process of reionization. Okay, so that's why we have to move beyond this E-mode bump. So obviously on the left, you can see that the curve is going above 1, and that's actually because of the helium reionization process that I mentioned. So it's just a way this plot has been normalized. Okay, so that's the reason why we have to move beyond those E-mode bump, EE or TE signal. And now we talk about the kinematic SZ signal. Okay, so kinematic SZ signal is really sensitive to reionization. So this is a plot from simulation from Nick Battaglia and others. So what this plot is showing is that when you change the process of reionization, the KSZ signal changes, and as you can see on the top, you see the simulation, and in the bottom you see the power spectrum of the KSZ, which actually changes when you modify the process of reionization. Okay, so this is great. So it just means that if we observe KSZ, we can learn about reionization. Unfortunately, KSZ is really subdominant compared to everything else that we have in our data. And to emphasize that, I've just highlighted the vertical axis on this plot. So you can see that this plot is in linear scale. The vertical axis goes from roughly 0 to 4 microkelvin square. But in the next plot, I'm going to show you what we actually see in our map. Okay, so now you see that this plot has the vertical axis in log scale, and you can see the extent goes from 0.5 microkelvin square to few hundred microkelvin square. And in this particular space, KSZ is flat, but you see signals from primary CMB and astrophysical foregrounds are completely swamping the KSZ signal to noise. So what this means is that KSZ can never be observed with signal to noise greater than 1 on any scale. Not now, not in the future. So we just can't do that, even with very, very sensitive instruments because of foregrounds. However, statistical detections look pretty promising. So if you take the cumulative signal to noise on this plot, it's actually pretty promising, as you can see in those 2 papers that are referenced there. So the statistical significance is actually extremely high for future KSZ measurements. Okay, so this is power spectrum. However, I mentioned those 2 words, which are reionization is an Apache process, and it's very non-Gaussian. So that means, why do we have to actually stop at power spectrum? Okay, so if something is just Gaussian, and if it's just random Gaussian, you can stop at the power spectrum because variance quantifies everything about that particular process. But if something is non-Gaussian, we have to move beyond power spectrum. So this was pointed out in 2016 by Kendrick Smith and Simone Ferraro. So what you're seeing here is the tri-spectrum of the KSZ signal. In particular, you're seeing the derivative of the tri-spectrum as a function of redshift. So the horizontal axis is redshift, vertical axis is the derivative of the tri-spectrum. And now you see that this tri-spectrum actually has it's bimodal. And the reason for that is because KSZ comes from 2 components. So you can see that there is a component that peaks at high redshift, so that's the reionization component. There is a component that peaks at low redshift, so that's the local KSZ. Okay. Now the other thing that you can see here, that the high redshift KSZ is much more prominent than the low redshift KSZ when you're looking at the tri-spectrum. So there is a reason for that. I'm not going to mention that right now, but maybe we can discuss it later. Okay. So basically, what I'm trying to say here is that when we're looking at the tri-spectrum measurement of KSZ, we are mainly probing reionization. Okay. So we took that paper, and then we tried to do this earlier this year with SPD data. So the estimator that we use to get the KSZ tri-spectrum is very similar to CMB lensing. So it's a quadratic estimator. This quadratic estimator is now going to pick up large-scale velocity-induced correlations of small-scale clustering of matter. So it's very similar to CMB lensing. So what you're seeing here is on the left is the simulation and right is the data. So obviously they won't look exactly the same, but the statistical properties look pretty much the same. So now if we make this more quantitative, so this is basically the trispectrum measurement from SPD. So the green points are our measurements. The black violins are scattered coming from 100 different simulations. And the black line is the mean of all of those 100 different simulations. So you can see that the green is really consistent with all those violins. So, and the green is roughly 10 sigma away from 0, which means we have measured the trispectrum. We have measured the trispectrum with roughly 10 sigma. Very consistent with SIMS. Unfortunately, the SIMS don't have KZ in there. Okay. So we are measuring a trispectrum and we are consistent with SIMS, but the SIMS don't have KZ. So what we are measuring is the residual CMB lensing and residual foreground contamination that we have in our maps. So we optimized our analysis to make sure that these things go away. If we don't do this optimization, we'll actually measure this at 100 sigma. Okay, so we did optimization. We tried to get rid of most of these things, but they are still present. So if we, for example, if we just subtract this black line from the green data points, you can see that the green data points will all now just be consistent with 0 within the error bars. So this is a non-detection. So we don't have a detection of the KZ trispectrum, but using this non-detection, we can actually set constraints on reionization. Okay. And that's what we try to do in the paper. So this, and when I say constraints on reionization, I'm mostly just talking about these two parameters because we're not sensitive to other parameters right now. So these two parameters are the duration of reionization. So this is the redshift duration shown in the horizontal axis. And the vertical axis shows the midpoint of reionization. So that's the redshift at which the universe was 50% reionized. So as you can see, just with KZ 4 point, we don't do a lot better. These two parameters are just super degenerate. Okay. But that's not the end of the story. Okay. So we don't just have KZ and Planck, but we actually have high redshift observations of Lyman alpha. We have measurements of high redshift galaxies from HST and now from JWST, which kind of tells us that universe was fully reionized around redshift 5 to 6. Okay, so this is called the Gunn-Peterson trough. So now we can make this plot again. So this is again the plot of the reionization history of the universe from different measurements made by astronomers. So here there is a point at redshift 10. You shouldn't take this point really seriously because I think this measurement has changed over the last few months. So just take this measurement with a pinch of salt. So that's one measurement saying that the universe is just fully neutral around redshift 10. But then we have some low redshift observation which says the universe is now reionizing. And then we have this data point which says the universe is just fully reionized around redshift 6. Now if we add more and more points, they're all just consistent with the ionization fraction being 1, meaning universe is now fully reionized. So now if you take that as a prior, and if we compute what we will get from our data, this is how it looks. Okay, so this is basically the constraint that we got from KZ, combining with the Gunn-Peterson trough prior. And you can see it's now just mostly consistent with all these other high redshift observations, which is good. However, the error bars are large. So the real question here is that how will the future high redshift JWST data points look? So I think there are some papers that are pointing out that there are already discrepancies, that JWST is observing some high redshift luminous galaxies that we don't actually expect. There are some couple of references there. So this is going to be another really interesting aspect that we can probe in the future. And KZ is going to be a key because KZ is going to limit the high redshift tail of the reionization process. Okay, so now going back to the previous plot, if we just include all of this information here, so you can see here when I include that Gunn-Peterson trough prior, we basically exclude all of this region. So we are now just sitting in this region, and with that alone, we can set constraints on basically upper limits on the duration of reionization, and we got it to be 4.5 at 2 sigma. So for this measurement, we didn't use Planck low L measurements. So this is independent of Planck measurement. but it's consistent with what Planck has produced. So with this non-detection, so we don't have a detection, but just with this non-detection, we have already excluded some very slow and early reionization models. So that's the result from this paper. So this paper got accepted in PRL 2 to 3 months before. Okay, so that's current, but the future is actually really good. So what I'm showing here is the forecasts from KSZ for SPD and future CMB experiments, like SO and CMB-S4. So on the left, we are seeing constraints from KSZ power spectrum. Middle, we are seeing constraints from KSZ tri-spectrum, and on the right, we are seeing a combination of all of these things. So KSZ alone does not constrain tau very well. But the nice thing is that the 2-point and the 4-point have different degeneracy directions. And as a result, when we are combining them, we actually add information, and that's going to add improvements to the final constraints. So in our current result, this is the result. So 2 sigma is 4.5. So 1 sigma is roughly 2.25. But the future, the expectation is that the 1 sigma for duration is actually 0.5, which is really great. And this is not constrained currently by Planck. So KSZ really is going to add a lot of information in terms of reionization in the future. So it's not only improving duration, but it's also improving the constraints on tau, which actually also has implications for neutrino mass. There's also a lot of potential to do cross correlation with intensity mapping, like 20 centimeter and so on with KSZ. Okay. Okay, I think I'm almost running out of time, so maybe I'll just quickly go through the TSE, if that's okay. Maybe I'll take 5 more minutes, if that's okay.
Okay. Yeah.
Okay, great. Yeah, thanks. Okay, so this is a work in progress. So this is science using thermal Sunyaev-Zeldovich effect and how we can infer baryonic feedback from that. So like I said before, the thermal SZ is the inverse Compton scattering of CMB photons by free electrons in hot intercluster medium. So that's why this the signal appears as a decrement, and this is how we detect galaxy clusters. Okay, so I'll just quickly show this plot. So this plot shows a forecast for future CMB experiments. Okay, so our current and future, so SPD, SO, and CMB-S4, compared to the current SZ selected cluster samples that we have. So this is the total number of clusters that we can detect as a function of redshift on the horizontal axis. Vertical axis is the cumulative cluster counts. So what you can see here at redshift 1.5 or so, we are going to detect few hundred to few thousand clusters from SPD and SO and CMB-S4. Okay, so this high redshift is really the unique discovery space, because the low redshift is going to be fully covered by future surveys, future optical and IR surveys, like, for example, LSST. We can also do cosmology with this, but I'm going to just skip that. I'm going to get into this. So we can do cosmology with clusters just by detecting clusters, but we can also look at the power spectrum of the thermal Sunyaev-Zeldovich effect. Okay, and so I want to show this because there is a growing discrepancy here between large scale and small scales, and I'm trying to emphasize that here. So again, you're seeing the power spectrum of the thermal SZ signal, and on the left side, so the large scale, so you see measurements from Planck, and then at L of 3000 here, you see measurements from ACT and SPD. Okay, so you can see that the brown band basically is an extrapolation of Planck, and you can see that the band actually does not match with the small scale measurements from ACT and SPD. Okay, so this again could be a real physics, or this could be systematic. So let's now try to see if we can solve this by modifying physics. So we can modify cosmology. So when we modify cosmology, the thermal SZ signal changes. Okay, so in this particular case, I'm modifying the neutrino mass, and you can see, for example, the dark red line maybe kind of goes through both Planck and ACT and SPD points. It doesn't go through fully. I mean, it does not agree with Planck on large scales, but it is much better than, for example, the green colored line. However, that dark red line actually has a neutrino mass of 0.48 eV, which has already been ruled out by several other things. So, so this could be a physics beyond Lambda CDM, maybe a little bit, but not everything. So you can also do the same thing with, for example, like sigma 8 parameter. Now we can try to do astrophysics. Now we can try to change astrophysics. So now what I'm showing here is a plot from simulations where we have now tweaked the AGN feedback. So this AGN feedback, what it does is actually just pushes gas out of cluster centers. And as a result, we get a suppression in the TSE signal on small scales. So in the previous plot, you can see that changing in neutrino mass does not really change the tilt of the power spectrum, whereas changing the baryonic feedback actually changes the tilt of the power spectrum, okay? But again, you can see that there are these three curves, but none of these three curves match Planck and Acton SPD, okay? So this could also be possible to some level, but it's not the full answer. That could be something that's probably beyond all of these things. So this particular fact actually has implications on structure formation, in particular the S8 tension. So what the S8 tension is that, so we have a measurement of sigma 8, a combination of sigma 8 and omega matter from CMB lensing and galaxy surveys, and they don't agree with each other, okay? So what you're seeing here are the CMB lensing points or those gray data points, and the galaxy weak lensing points are coming from either KITS or DES, and you can see that they actually don't agree. So to make them agree, you have to introduce some new parameters, or you have to get rid of small scale information, okay? So this could be some new baryonic physics that we don't understand, or this could just be a systematic, in either of these data sets, okay? And here is a plot showing, just emphasizing that particular fact again. So this is a ratio of matter power spectrum from two different set of simulation, one which has baryons and one that does not have baryons, okay? So adding baryons, it changes the power spectrum, particularly on small scales, okay? So that's a ratio plot. And you can see on large scale, they're all just consistent with one, but when you go to small scales, they're all just all over the place. So in particular, I'm plotting three different simulations here, okay? And this is actually not surprising because these simulations don't agree with each other, but there is no reason that they have to agree with each other because we don't have data to calibrate these simulations, okay? So that's where this TSE and future measurements are going to play a key role. So this is an analysis that we are doing currently. So this is again combining data from different SPD surveys and also combining data from Herschel satellite. So what I'm showing here is that the thermal SE power spectrum is actually sensitive to parameters that that govern structure formation like neutrinos and also the baryonic feedback. So this is the same plot that I've showed before, but now just putting everything together along with some expected error bars from the current measurement that we're doing. So on the left, you're seeing how the power spectrum changes when we modify neutrino mass. And on the right, we are seeing how that changes when we modify the baryonic feedback. And the black error bars that are placed on those green curves are the expected error bars for this particular measurement. So you can see when we do this measurement, we can actually already rule out some of the baryonic feedback models, okay, depending on where the TSE power spectrum happens to lie. So this is current measurement that we are doing, but the future looks extremely promising, okay? So these are the error bars in our current measurement, and these are the error bars that are expected in the future. So what's going to happen in the next few years is that we're going to have all of these sensitive measurements, and then we have to basically just recalibrate all the SIMs that we have currently. Like I said before, it's not surprising that the SIMs don't actually match with each other because we don't have data points to calibrate these SIMs properly on small scales. So that's where these future measurements are going to play a really key role in calibrating these simulations. So this is power spectrum of thermal SZ, but we can also do cross correlations. So for example, here, what I'm showing here is the expectation for SPD when we cross correlate CMB lensing with galaxy weak lensing on the left side, and then Compton Y, which is thermal SZ with galaxy weak lensing on the right panel. You can see these error bars are so small that we are going to get extremely high detection significance of all of these signals. And these signals are probing small scales where we are extremely sensitive to physics from baryonic feedback. So we're going to have all of these measurements in the next few years, which are going to play a crucial role in calibrating a lot of baryonic or hydrodynamical simulations. And that's where the future is going to go in terms of these astrophysical parameters. Okay, so that was my last slide, and I'll just summarize now. Sorry for going a little bit over. So SPD3G is an excellent instrument for mapping mostly the secondary anisotropies of the CMB. We just put out our recent results from the first 2 years of observations, where we have the most precise measurement of the E-mode, polarization, and lensing on small scales. So SPD3G is also crucial for doing delensing for BICEP. We get roughly a factor of 3 improvement with relensing compared to BICEP alone. So that's with the current planned SPD observations. But SPD is also going to go until 2029. And with those observations, we will actually get something like a factor of 5 to 6 better improvement. So this is sigma R 10 to the minus 3. So not as good as CMB Bharat is expecting, but it's almost there. So noise levels for SPD is very similar to CMB-S4. So SPD is a really good test bed for identifying systematics that will be important for future surveys. And with the synergies that we have, there is a lot of potential for cross correlations with future galaxy surveys, CMB surveys, and intensity mapping instruments. So then I presented results on KSE, the first results using the KSE trispectrum. And then I showed how KSE is promising for future. And then thermal SZ, I didn't talk too much about clusters, but I showed some results where we're trying to constrain baryonic feedback and also cosmology with a robust estimation of the TSE power spectrum. I'll stop there, and I'll be happy to answer more questions. And thanks so much for patiently listening. Thank you, everyone.
Thank you, Srini, for a nice talk, and the floor is open for questions.
Yeah.
Please raise your hands if you have any, or just feel free to take the mic. Yeah. Shubha.
Yeah.
Hi, Srini.
Hey.
Thanks for a very nice talk. I had just one question. If you go to your something, I think you said something very provocative. So let's go to page 70. Okay. Now 70.
70. Okay.
That's right. Okay.
Yeah.
So now the claim is that when you have very low error bars, you will be able to constrain your simulations to have the proper physics or whatever. I mean, that will then go and feed into other analysis. Now, if you look at the data points which you get from the secondary CMB, it is way low below. So given that if these data points are not wrong, error bars will shrink around this data point.
Yeah.
And then do you have any physical model which is even beyond high AGN that can suppress, that can have, I guess, something which will peak at 1,500 and suppress it so much that it goes to 3,000. So is there anything progress over there?
Yeah, so that's a really good question, and that is exactly why I'm currently doing this analysis in a slightly different way compared to what was done there. So I'll show you this plot for that. Okay, so this is sorry. Let me just do this. Okay. So this is basically a plot from the HIL. So those measurements that you're talking about, right, on small scales. So those are the ACT and SPD measurements. So those measurements are done in this way. So what has been done by both ACT and SPD are, so we have these auto power spectrum and cross power spectrum from our 3 bands. So the data points are all there. Okay, so and then we have this fit. This is a black color, which is a really good fit to the data points. But the fit actually has components, different components, and most importantly, it has this orange line, which is the signal coming from cosmic infrared background. So what has normally been done with all of these measurements is that we have just assumed a template for these signals, and we just constrain the amplitude at L of 3000. Okay, so we don't have any L dependence for any of these curves. So the only L dependence is coming from this template. So you can imagine now, if the template for this is wrong, it's going to bias all the inference that we make about either TSE or KSE, right? So we have to be very careful because these, like you're saying, the error bars are going to be so small that we are going to be so much dominated by systematics, and we have to be extremely careful in the way we interpret these measurements. So the way I'm doing this particular analysis is not by just taking this and fitting a template, but by trying to use the the frequency dependence of all of these signals to get rid of most of them, and then look at, so basically like do a internal linear combination, where I basically just project out some of these signals using their frequency dependence, so that their contamination is actually really low in our final data set. And so I really think that these points are going to go up if we do those analysis properly.
But if you're missing, okay, so to go back over there, so there are like, let's say 5 different things that you put in.
Yeah.
Suppose you are missing one more, then that will again put the thing down.
Yeah.
Right.
So that one more
thing I
can,
can
for
see over
example,
here that's missing over here is basically you have radio Poisson sources, but there are these radio cocoons, and they will have power over here as well at this kind of values, and so that will
so yes, exactly. So I was going to say about like radio TSE connection. Just I guess what you're mentioning. Yes, so there could be new signals here that can then increase the amplitude of the thermal SZ. And there could also just be some kind of systematics that we are completely ignoring here. So the main goal of this particular paper is more than constraining these baryonic feedback. We just want to give out these data points to the community, so people can plug in their own models with some new components that we might be missing right now. So that's one of the major goals, and I think that'll be critical for any future development on the high LTSE, I think. Yeah.
Right. Good.
Yeah. Thank you.
Any other questions? Okay, so I can ask one quick question. So you mentioned about so the question can be like this, like, can we get better constraints for, let's say, primordial non-Gaussianity from SPT measurement? So I'm asking this because so you mentioned about the KZ and the trispectral measurement, non-Gaussianity, etc. So understanding the non-Gaussianity of these secondary anisotropies, will that be helpful for the primordial non-Gaussianity measurements? Yeah.
Right. So there are two ways that can enter. Okay. So one is that, well, first thing I'll say is that the primordial non-Gaussianity, if we just take the trispectrum of the CMB, so SPT is not going to be great there because we are not a full sky survey. So we're not going to be competitive with Planck. So that's the first thing there. The next thing is, yes, so even before going into the trispectrum, we can actually use the secondary anisotropies to improve FNL. So one of the thing is that, so for example, if you can actually do FNL with galaxy power spectrum. Okay, so you can take these future galaxy surveys, and what you can measure is this thing called the large scale galaxy bias. So the large scale galaxy bias basically just comes from the if it's just single field slow roll, which does not predict a lot of non-Gaussianity. Does not, some different models for the inflation actually predicts this large scale galaxy bias. And so when you take the galaxy power spectrum or the matter power spectrum from galaxy surveys, you can actually measure FNL. But what happens is that on large scales, it's going to be sample variance dominated. But if you include KSE information, or if you include CMB lensing information, there is this argument called sample variance cancellation. So this was introduced by Uroš Seljak in 2008. So what is proposed was, instead of just looking at the galaxy power spectrum, which is a biased tracer of matter, you can actually take the ratio of two different observables that have different biases. So for example, if you take CMB lensing, it is an unbiased tracer of matter. So instead of taking the power spectrum of just the galaxy alone, you have to take the ratio of galaxy to CMB lensing. You can also do that with velocity reconstruction using KSE, because velocity has a different bias, but it's not the same bias that the galaxy is tracing. So when you take the ratio, you can actually cancel the sample variance there. So that is how secondary anisotropies of the CMB are going to improve FNL constraints. In fact, a paper just appeared on the archive today. So that's basically improving. Yeah, I think it's FNL with CMB lensing and galaxy surveys. Yeah, but that's how KSE, for example, can play a role in improving FNL.
Mhm.
Yeah.
Okay.
Yeah.
Any other
But the
questions?
price spectrum we are looking here for KSE is it's not going to be like too sensitive to FNL, because these are all mostly just coming from low redshifts.
Mhm.
Right? So it's not really like primordial trispectrum.
Okay.
Yeah. Thank you.
Yeah. Any other questions? Yeah, I don't see any other questions here. So if not, let's thank Srini again. Thank you so much for joining. And yeah, I thank all the participants also for coming. Yeah. Okay, let's find it up. Thank you.
Yeah.
Bye.
Thanks, everyone. Bye.